Hello, everyone. Welcome. Today, I will present to you about ZFS Direct I/O benchmarking pitfalls. So it will be a bit about ZFS, a bit about benchmarking, and about pitfalls as well. So how to avoid unpleasant situations when you benchmark. My name is Mateusz Piotrowski. You may know me as 0mp at freebsd.org. I am based in Berlin. I've been a FreeBSD user since 2016, and I got my commit bit in 2018. And since then, I've been working professionally on FreeBSD. Nowadays, I'm mostly focused on OpenZFS. But my areas of interest are ports, RCA, so the init system for FreeBSD, ZFS, and benchmarking. So if you want to talk about those things and others also, hit me up. So the main idea of this presentation is not holding direct I/O wrong is a great first step to potential performance gains. So I'm not promising you to show you how to improve your machines with direct I/O. This is specific for every workload. What I want you to do today is to understand how to approach direct I/O so that you can even start measuring if it's good for your workload or not. And we'll go through 3 chapters today. First, I'll give you a quick refresher on how ZFS behaves and what it is and how to think about it. This will help us to understand what the pitfalls are when we are benchmarking direct I/O. And then we'll have a brief look at the implementation details of direct I/O, how it tries to be a good citizen in the ZFS world. So this is roughly the overview of what we are going for. So let's get started. So ZFS 101. The architecture overview. So what is ZFS? So it's a copy and write file system. And in contrast to traditional file systems, which are, we may maybe call them overwrite on write, copy and write is always, when you are updating a file, you never overwrite the blocks in the same place. You always find a new place on the disk where it's still free, unused, and this is where you save your new bytes. And it unlocks pretty exciting features. I'll tell you more about it in a moment. When it comes to the history, it was developed at Sun Microsystems in 2001, and it was imported into FreeBSD in 2008. The story how it got ported into FreeBSD is a very interesting part of our FreeBSD lore. You should look it up. It's a great feat of engineering. And then, as of this year, FreeBSD is using OpenZFS. A couple of years ago, we switched from having our own fork of ZFS in tree to collaborating together with other operating systems on the OpenZFS project. So we get one code base that we can run and test on different platforms, operating systems, and so on. So that's where we are. So what can ZFS do? So we have a couple of interesting things there. For example, it takes care of data integrity. So it checksums all the blocks, which means that if you have a corruption on your disk or your memory is faulty, then ZFS has mechanisms of detecting that and potentially correcting them, but it will tell you that something is off and you have a chance to act on it, which is pretty great. It also has data consistency. So what it means is that when you are updating a file, you never end up with a partially updated file. It's either an old version or a new version. So if you have a power a power breakage, let's say, in the middle of updating a file, then ZFS, it will not save partial results. You will always have a consistent state no matter what. And then it also gives us pooled storage, so you no longer have to partition your disks beforehand. You just throw all your disks into one pool. You can then design your layout. You can mirror some of those disks. You can use some cool things like RAID Z. And once you have all of that, you have a pool of storage where you can create data sets, and they can grow and shrink. And if you want to move files from one data set to another, you can freely do it. It's gonna the storage is gonna flow where your data is. So that's pretty neat. So ZFS is pretty awesome. It also has things like snapshots. It also has efficient remote replication. So if you have, you don't really have to like send all the bytes over the network if you want to have the same contents on a different machine. Like if you are iteratively keeping two machines in sync with ZFS, you just send like diffs of data sets, which is very, very handy. It also has compression. So you don't have to zip your files to save on the storage. ZFS can do it in the background for you. And you can choose from different compression algorithms. It's pretty interesting because apart from saving storage for you, so you can save more data, it can also speed up your workloads because you, if the data on the disk is well smaller because of the compression, then you effectively do less I/O to get it from the disk. So if your disks are slow and you compress your data well, then everything speeds up. It also has cool things like deduplication. So if you have various files with the same blocks in them, then you can save just one copy of a block. It's sometimes used. It has some caveats, but it's there. And then of course RAID-Z, so different layouts for your pools, where you can have different levels of redundancy of disk and so on. Quotas, all the cool stuff. Boot environment, so that if you upgrade your system and it doesn't boot anymore, you can easily boot back into the boot environment before the upgrade, and you can resolve your issue from there. You don't have to pull out a pen drive from an ISO or like a CD or whatever and like rescue your machine. You can just kind of boot back to where it was still working and then figure out what went wrong. So it's a very powerful file system, which is also why it's sometimes difficult to integrate new things into it, because you have so many other things to take into consideration that are already working in it. Yeah, so it makes sometimes implementing things a bit more challenging. And then we also need to take a look at different layers we have in ZFS. So we are only going to look at this very simplified view of what ZFS looks like inside. So this is on the kernel level. At this point, we already got an I/O request, and we are arriving at the ZPL. So what it roughly does, it translates the VFS request calls into ZFS-specific internal machinery. Then we hit the DMU, and at this point, we can choose if we want to go the direct I/O path, skipping the cache, the ARC, or we want to go the buffered path through the ARC. And once we decide, we end up in the very same place, which is the I/O pipeline that orchestrates all the read and write operations, and then there are some other layers beneath that. But essentially, direct I/O only operates on this one layer of this whole big stack of what ZFS does inside. And the ARC is actually one of the most, I guess, famous parts of ZFS because it's so powerful. It's caching things, and it's very important for ZFS because this is where all the performance, or like a lot of the performance lies. So it's useful for caching. It balances between most recently used and most frequently used. So the nice thing about this cache is that it adapts to your workloads. So depending on your workload and how often, how you use files, it's going to adjust to that and support you in the best possible way. It also keeps track of various useful metrics, so that you can then tune it to be even better at what it does. For example, it has ghost lists. These are super cool. So what they do is that sometimes you have a machine where you have, for example, little memory. So, and when you have a very heavy workload, it will happen that sometimes when you have a file cached in the, well, when you have a file in the cache, and then you have many more files coming in, you will have to evict this file from the cache. And then if it turns out you actually want to use this file again, but it's not in the cache anymore because it was just evicted, the Arc takes note of it and increases the metric called like ghost hits or something, which means that if the file was there, if I didn't evict it, you would have a hit, but it wasn't there, so I had to go to the disk. So I don't know, consider like retuning me or add more RAM or do something about it, potentially. So that's nice. It also uses as much RAM as it can, which is also great, and it's very aggressive about it. But at the same time, it backs off when it needs to. So when you think about it, it's the trade-off in the Arc is that you get better latency and throughput, but you pay with CPU and RAM. And this is exactly what people want to avoid when they use direct.io. So direct.io is essentially a flag that you add to various function calls, like read and write. It was first introduced in ZFS for database workloads for the purpose of bypassing some of the caches to prevent unnecessary I/O. So for example, they wanted to avoid read ahead, so prefetching data. Unfortunately, it's not standardized, so there is no single document explaining what you can expect from the direct.io. Everyone is doing it in a slightly different way. There is a consensus how to do it, but it's like you can't really refer to a document and say that this is how it's supposed to be done. So OpenZFS developers reviewed various available documents like the Linux Open manual page and followed various conventions, look at like how other file systems implement that, and came up with like a set of features and assumptions and whatnot to make it a reasonable implementation for direct.io. When it comes to who benefits from direct.io, or like what benefits from direct.io, so there are a couple of things. Some examples are applications with their own caching, like databases. So having like multiple caching layers that are not aware of each other may lead to problems. So disabling caching when you have a database with its own cache may lead to performance gains. You also have workloads that I would call write and forget, like application checkpointing. So imagine you have a computation that's running for like a month or so, and you really don't want to lose all the results if there is a power outage. So you save the partial results every now and then. And when you're doing this, you're not really planning to read it anytime soon unless there is a breakage. So you just want the data to reach the disk as soon as possible and then free up all the resources back for the computation that you're running. So in this case, having a cache all the data you just wrote makes no sense. Same for read and forget. So when you're restoring from a backup, you just want to restore everything as fast as possible. You don't want to, cache all the different files in the cache and like with a possibility to read them in a moment. You're not going to do that. So direct.io could also help in this case. And direct.io is also getting quite popular recently because of NVMEs. So it's not that direct.io is only useful for very fast pools, but certainly with faster hardware, the overhead of Arc is no longer negligible. So you can see actual benefits of skipping the Arc and just going direct.io. There are higher chances if you have NVMEs in your deployment that direct.io is going to do nice things for you. No guarantees, but higher chances. Right, so chapter 2, Pitfalls. So in this chapter, I will lead you through a benchmarking setup I prepared for the purpose of this presentation. And first, we'll start with explaining the setup, so what we're dealing with. So the hardware I used was just a laptop T480 with not too powerful processor anymore, 16 gigabytes of RAM. The disk I used for the benchmark was a CFast card connected with a USB. So it's like a small card. It's yeah, it was good enough for the tests. For the software, I was running FreeBSD 15. ZFS is 2.3 something. The important part is that direct I/O is already implemented in this version. The record size of the pool was 1 megabyte. And I used FIO for the workload generator and Hyperfine for orchestrating the benchmarks. And on the right side of the screen, you see the FIO job file. So when you want to benchmark your things with FIO, you can write a job file, and it looks roughly like this. So you have a global section on line 3. This is where we have like common variables for all the other workloads I defined later on. So group reporting is something about the output, doesn't really matter. Nsync makes the workload call an fsync at the very end to make sure that all the data actually reach the disk. It's also a sequential write workload, so we are trying to write as fast as possible, not trying to like randomize our writes, but like get everything from the disk that we can. 4 jobs, block size is 128K. So this is the size of our requests. And in this case, we have a file size of 128K also, and we have like 1,000 files. And then we have 3 different workloads. We have the raw that goes all like directly to the disk, no ZFS involved. Then we have the direct workload, where we are writing to a pool with the direct flag enabled in FIO, so FIO will try to do direct I/O calls. And we have the buffered, which is like the standard way of going through the arc, right? So FIO is just behaving like a standard application. Right, so we run the numbers. We run the buffered at the top. We run direct at the bottom. And it looks roughly the same, right? So in a way, you can think that, OK, so no performance gains for me today from direct I/O. And this is a wrong assumption. So if you start investigating and you look at the I/O stats sysctl, you'll see that there were no direct calls performed at all. And I was, OK, that's curious, because we enabled that. So why it's not there? It turns out that you have to enable direct I/O before you do anything. So OK, so there is a sysctl for that. DIO enabled. I think it will be on by default in FreeBSD soonish. But for the time being, you have to enable it. OK, so cool. So we do it. So now ZFS is allowing direct I/O. We run the numbers again. And still, no direct I/O, no bytes, no count, like nothing. Like ZFS is not registering any, not letting through any direct I/O. OK, so we have the job file. We make sure that like the property for our data set is actually allowing direct I/O. Standard says it is. Does any one of you see a problem here? What could be wrong? So let's fix that. Iteration number 2. It turns out that direct I/O is ignored if a file is smaller than the record size. So we had very small files, 128K. Our record size of the pool was 1 meg. So in order to avoid read, write, modify cycles, and which decrease the performance significantly, the consensus in the development community was that we should not, like if someone requests direct I/O for small files, let's let them through the arc. It's going to be a better call, and that's how it works. So OK, let's try something else then. So now we do one file per FIO job. We do big files to make sure that we have like files that are big enough. So 4 GB. I also set I/O size to make the benchmarks shorter. And then the offset increment helps me with the raw disk. So when I have a pool, I have 4 files. But if I write directly to the disk, I have just 1 file. And without the offset increment, all the jobs would write at the very beginning of the disk. So that's not ideal. With the offset increment, I make the 4 jobs write in 4 different places of the disk. So it just makes the benchmark more reasonable. So we run the numbers again. We look at the numbers, and it's still the same. And then it's OK, fine. We've been here before. So we check the I/O stats sysctl, and it's 0 again. Like, OK, that's not great. So we iterate further, because it turns out that ODirect is ignored if the issued writes are not record size aligned. So when you're writing and your requests are not aligned with the record size, you're also ignored. So it's like, oh, OK. So you see, like, there are various places where even if you enable direct I/O and you specify that you want to use it, if your application is not fulfilling those requirements, you won't see any direct I/O traffic. So all right, so let's make sure that our requests are big enough. So we go for 16 megs, and we run the benchmarks. This time I included the results for the raw workload, and it all looks roughly the same, which means that we are most likely reaching the limits of the device, because like the raw workload, which is testing the maximal capacity of the disk, is basically the same as our buffered and direct I/O performance. So there is nothing really we can gain from setting direct I/O. Cool. So this can also happen. And just to be sure, we take a look at I/O stats, and now we can actually see that there are direct I/O requests going through. Cool. So let's try one more thing. This is all quite exciting, right? We got direct I/O to actually do something. So let's see if we can modify our job file so that we can see what people want to see from when they decide to test out direct I/O, right? Because usually you have a disk that is capable of performing very fast, but your experience shows that your application is not achieving that. So you're like, OK, with direct I/O, I'm going to skip all the clutter and just like go for the maximal performance. So let's try to see if we can have something like this. So I set the block size to 1 meg. And now when you when you see presentations of people who benchmark direct I/O for their use cases, then this is roughly what you usually see. So you see the raw performance performing very well. You have the buffered one that performs worse, and you have direct that performs somewhere in between. So that's usually what you want to see, as in you wish you see it when you apply direct I/O. But it depends on the workload, of course, right? Not every workload can be sped up with direct I/O. But finally, we see a difference. That's pretty nice. So in summary, there are a couple of things to take into consideration when you're benchmarking direct I/O. So first, remember to activate it. This is very important. Avoid small files. So when you have your application and you want to use direct I/O, make sure that the files you're writing are, like you have to check your record size, the size of the files you're writing, and then check if your I/O fulfills the alignment requirements. These are all things that you may maybe not thinking about, but if you want to check out direct I/O, first review those things in your application. Also, disk raw performance, like you cannot really go above that with direct I/O. If you're using the buffered path, maybe if you're serving everything from the memory, then you'll have wonderful numbers, right? So you can have a lot better performance with the buffered path. With direct I/O, you are capped at the disk's raw performance. And yeah, usually with faster hardware, you are more likely to see benefits of direct I/O, but that's like also possible to see it on hard drives. So let's take a look at the implementation details. How does direct I/O fit ZFS? How is it trying to be a good citizen that is not breaking everything that ZFS promises? So there are like various little things that are all kinds of little implementation details. So for example, direct I/O does not imply authing. So when you are issuing direct I/O, the only thing it does, it skips the arc. But it's not making the bytes land on disks straight away, right? You can still choose if it's a synchronous call or an asynchronous one. Maybe the name direct I/O is a bit misleading because it feels like when I'm using this flag, my bytes just go directly to the metal, straight there, and it's just skipping all the like unnecessary things. But that's just not the case. Also, indirect blocks, so all the metadata, they are still buffered. Direct I/O is only about the user buffers. So if you have a workload where you are dealing with a lot of metadata, then it's also possible that you won't see any performance gains, or like it's also something to take into consideration. Like direct I/O does not turn everything into like it does not turn off the arc, right? The arc is still there and is doing a lot of important things. Interestingly, apart from the standard setting that is on by default, we also have the always setting, which means that ZFS will do its best to kind of treat all the I/O from your application as direct. So if you have an old application and you just you don't want to rewrite it, or you just want to test if direct I/O would benefit it, then you can set direct to always and see what happens. It's pretty handy. Right, so also the alignment requirements are different depending on the I/O. So for write I/O, they're a bit more strict. For reading, not so much. The important part is that whatever happens, ZFS will make sure to keep our data coherent. So by using direct I/O, you're not sacrificing any of the safety. Your data is still safe. Other important things are like that mmap files, they are always buffered. And also, if you end up using direct I/O and then also modifying the same buffer within the same transaction group, it won't wreak havoc in ZFS. ZFS will detect that and redirect your calls to the arc. So everything is going to be all right there. You don't have to be careful when you're using direct I/O. ZFS will make sure to protect your data. And there are also some unimplemented cases. So for example, Direct.io doesn't work currently on ZVols, and it's not possible to mix the application with Direct.io writes. So it's, again, another small thing that you have to keep in mind when you are testing it with your deployment. So in summary, Direct.io is relatively easy to use from the user perspective, right? You just enable a couple of sysctls, or just like one, and it's going to be on by default soon, so no sysctls for us. You can start using it very quickly, but then you should probably think twice and maybe measure 3 times before you deploy it, because it has various caveats. And it's a very powerful tool. It helps with performance for a certain group of workloads, but it's certainly not a bullet, like a silver bullet for all the performance problems. And I feel like it's often advertised as such. So when I was doing my bachelor's and I first heard about the Direct.io, I thought that like it's weird that we even have non-Direct.io, because like why would you want to do like extra things if you just can send your data to the disk? That feels so I don't know, simple and straightforward. And I think that that's the meme that's circulating around. The right alignment is critical also, and you should probably try tuning other things of other parts of ZFS first, like the arc, or adding L to arc to speed up your deployments. Direct.io is an option for optimizing your setups, but it's probably not the first thing to think about. And as I said before, ZFS with Direct.io will not eat your data. It's implemented in such a way that whenever there are some edge cases where we are overwriting a buffer that's in flight, or we have a file in the arc, but we also are trying to use Direct.io to overwrite it on disk, then ZFS will do the right thing and manage all of that for us, and it will, like, the data will be fine. Perhaps it will be a bit slower because our call will be redirected into the arc or something, but at the end of the day, it will all be fine. Thank you. That would be the end of my presentation. Yes?
Do you have some examples of typical use cases that would benefit from Direct.io versus not? Like when it has to be certain page sizes, is it database applications like Postgres, or what kinds of things would make you try?
So yeah, so the question, I think the question was if I know any workloads that benefit from Direct.io. Is that correct? So yes, as I mentioned, there's this group of different workloads. The databases are often good candidates for Direct.io, and situations where you really don't care about the cache. So you are just writing the data once or reading them once. In those scenarios, caching them for potential use in like near future doesn't make any sense, because you know you don't need this in the cache. So in those cases, these are the simplest ones. For more complex workloads where you are reading and writing, and sometimes you may want to reread the file, it may still be beneficial, but you have to check it on a case-by-case basis. Thank you, but it's a good question. Yes?
Do you know the difference at a more technical level between Direct.io, so calling read-write with ODirect, versus setting a property of your data set of primary cache and secondary cache both to none? Because that essentially disables caching altogether, right? Is there a difference there?
So the question is if disabling the arc or setting it to cache none of the things differs from direct I/O. It probably does. I don't have the answer at the moment. Maybe Alexander has.
Side, I was actually had some comments in that direction too. Direct I/O is a new thing. It's still being in development, and just recently, maybe months or two ago or less, I pushed one more interesting patch, which actually integrates direct I/O, not direct I/O, but ODirect flag with my earlier work done about a year ago, which I called uncached I/O. With uncached I/O, ZFS is instructed to reduce caching, not do all the paths through the arc, but reduce caching as much as possible, which means once data are written to disk, as soon as transaction commits, it's data emitted from arc. Same as on read. We can do speculative prefetch. We prefetch them. We can read them. No application can read them. As the moment application reads the data, they're emitted from arc. So we can do uncached I/O going through the arc. And part of that work earlier, when you set primary cache to metadata, all of your reads and writes still going through the cache, but they're getting evicted from cache immediately as soon as data, as soon as they're no longer needed. To setting primary cache to none is too extreme because metadata too often reuse it. When you read multiple blocks, you need indirect blocks again and again and again, and not caching them would be a waste. But primary cache metadata is interesting thing by itself, since it allows ZFS to save some memory copy in normal arc operation. It's forgiving of a few things, and it is actually faster doing that when you don't need actual caching. But it's actually went very well after integration with ODirect. As I was told, Direct I/O has a lot of limitations when it goes about alignment, about many things, and sometimes it's getting annoying because, as was told, direct equal to standard means it will fail if you do something wrong. But many applications, since ODirect is not exactly properly specified, not documented, different applications may have different expectations. And for example, for FreeBSD, it's right now impossible even to get those expectations from file system. On Linux, they recently okay. On Linux, they actually recently introduced variation to fstat, I think, fstat something, syscall, when you can get what is the alignment restriction for specific file to implement direct I/O. So now on Linux, you can properly know what to do right. FreeBSD at this point doesn't have this equivalent syscall, so you have to just hope and guess, and if you guess wrong, it will fail, which is not exactly a usable approach. That's why I think that I mentioned patch I implemented couple months ago, that actually wire ODirect, which is not good enough for direct I/O, so the uncached I/O. For example, you have your buffer not aligned, or you're doing small file I/O, or you're doing something else which cannot do direct I/O properly, and in that case, you'll get uncached I/O, which is still better, which is still faster than going through the cache. It will still not pollute the cache, not wipe the cache when you do like read once or write once workloads. You get all the same cache benefits, but without penalties of direct I/O, because direct I/O does have penalties in some workloads. For example, if you simply do not have enough requests to make your disks busy. If you have pool of dozen disks, but you're sending one request at a time, and obviously ODirect has to wait for request completion until it actually returns to application. It's uncached by definition. It's direct. So you have dozen disks, please send 100 requests, 1,000 requests, whatever, if your application can. If it can't, ODirect is likely not for you. But in that situation, uncached I/O can help, since you can still have read ahead, write back, everything works. And other things would be interesting to see on FreeBSD actually. Linux also got it very recently. I think it's last few months. It's been developed like 6 months ago, but getting landed only now. You can mark specific, I forgot, operation or a file with also, it's actually also call it uncached IO. I don't pretend on the name, but I was first. When you can mark something as a file or IO as uncached IO, and you write a file, and it will go through the cache, but it will evict immediately. And we could also actually implement that uncached IO without forcing direct IO. So that application can choose whatever they want, direct IO, great, uncached IO also fine. So there are some integration work still could be done, and it looks like should be pretty nice picture altogether.
I won't be repeating this. But thank you. That was a great explanation.
I had a maybe simple question. You said that we have a maybe simpler question. You said that we should not use direct IO. There's really no benefit if you have a lot of metadata in your IO operations that you're doing. Can you characterize a little bit more specifically what you mean by metadata?
So since you have indirect blocks always cached in case of direct IO, then if you have a lot of those indirect blocks, then what I meant is that the bottleneck may be somewhere else. So it might be one of the telltales that if you're not seeing improvements from direct IO, and you have a lot of those indirect blocks.
Yeah, so my question is a little simpler. Like, what situation would cause let's say a file on my file system to have those indirect block presence? Is it when he has extended attributes? Is it when he has ACLs on it? Is it when he has, like, what is the metadata, practically speaking, that causes that?
I think that one of the things could be if you have a lot of files in a directory, then the tree is then when you're storing this tree of all of the directory, then that's a lot of indirect blocks. So this could be just off the top of my head, and potentially a scenario like this. But in practice, I'm not sure if this is enough indirect blocks to really be causing this sort of a situation. So I'm not sure, but I would bet on the directories with lots of files.
Okay.
Yes?
Should we write something in tuning.7?
Yeah, definitely. But then the tricky part is that what would you write there? That there is direct. So there are, that's the thing. ZFS can be tuned in many different ways. I think we have an article on the wiki explaining some of the tuning tricks that you can do to ZFS. But ultimately, the defaults that ZFS ships with are very solid, and they are usually good enough for most use cases. And to tune ZFS, you really have to know what you're doing, because most of the time, when you just modify a random variable, hoping for it to help you, it will make things worse. So yes, documenting things is very important. At the same time, it could be a lot of false promises if written incorrectly. Yes, we have 50 seconds.
Sorry, to reply to both of you.
Yes.
You said there is an article on the wiki, but wiki, I think either no one reads it, or it's usually unmaintained, so it would be good to at least have it in the man page. The same article, just copy and paste it in the wiki, and say, do it on your own.
Yeah.
Be careful.
I think moving things out of the wiki is an ongoing project, and from what I've heard, there are plans to do something about our wiki. Maybe one of the solutions would be to move the content out of it. Yeah. Yeah.
Yeah, there's two issues with the wiki. One is it's
It is. It is very old.
The
Yeah.
other issue is there's a lot of data in the wiki that should be in the handbook. I know the first problem is being worked on. People say others are working on the second one, but I don't have any names who belongs to this group of others. So that might be an opportunity for people to improve the handbook or the appropriate
Yeah.
set of docs as well.
Definitely, definitely.
That's it.
Yeah, thank you. It could also be that this documentation should actually land in OpenZFS documentation. Then it won't get stale that easily, I think. Yeah. Cool. I think we ran out of time. Thank you so much for your attention, and enjoy the conference.